First, I want to thank Sue Chang for inviting me. I've always enjoyed talking with the computational science community about my work. I was delighted when I received Sue Chang's invitation. Now, Sue Chang took my course on computational methods at Stanford many years ago. Now, I presume the purpose was to learn how computations can be used in economics, because she certainly didn't need any mathematical instruction from me, certainly being a student of Michael Saunders. So my talk today is also aimed at giving you a highly condensed version of what Sue Chang has heard over the past many years about my efforts in bringing modern computational methods to economics. Now, I always like to begin talks, particularly with economics audiences, to emphasize how computation matters. And one of my favorite examples of where computation screwed up was the Tacoma Narrows Bridge, collapsed in 1940, where basically engineers had used a simple linearization technique to analyze the stability of a bridge in the wind. And this had worked for a long time. However, because of innovations in the construction and design of the bridge, it turned out that there were higher order nonlinear effects that were missed by the simple approach and led to this, this collapse. Now, the good news is these engineers spoke with the experts in fluid dynamics, structural mechanics, et cetera, and figured out how to do a better job. And we didn't see this again. The bad news is that the linearization methods that were behind the Tacoma Narrows Bridge collapse is the basic main tool that macroeconomists use to analyze complex dynamic economic systems. And this was the case even after the Great Recession. So that's a contrast between computational or engineering science and economics. Now, some of this may sound strange to you, particularly the older people in the audience. There used to be a lot of collaboration between economics and computational scientists, applied mathematicians. For example, Ken Arrow and Milton Friedman both worked in World War II think tanks, where they worked on what we now would call operations research problems, but which involved computation and which led to breakthroughs in statistics. Ken Arrow and other economists in the 1960s worked on optimization theory problems, and Ragnar Frisch, who was the founder of the Econometric Society and Econometrica, actually proposed barrier methods for linear programming in the 1950s. Now, that didn't go anywhere because in the 1950s, you only had single precision arithmetic, and also you did not have the kind of linear algebra software that was algorithms that was necessary to deal with the instability problems of barrier methods. But anyway, that was an economist who was involved in developing in the computational science literature. There's been little interaction in the last 40 years. Now, why do I say 40 years? Well, economists, when they teach constrained optimization, they always refer to the Kuhn-Tucker theorem and the Kuhn-Tucker conditions. Whereas computational optimization people, mathematical optimization people, now call it the KKT theorem, because in the 70s, the contribution of Karish was discovered, and then Kuhn led an effort to then make sure that this is called KKT, Karish, Kuhn, Tucker. But economists had kind of disconnected themselves from this world by that time in the mid-70s when that happened. And so when you look at computational writings of economists, you will see this, that there seems to be a disconnect with what's been going on in the last 40 years. The other thing is that they love Matlab on laptops. And of course, that greatly limits what you can do. Now, what I have been working to show is that modern computational science, hardware, software, et cetera, tools can potentially help advance economics. It's a potential. This is not consulting work where we know the answer before we do the work. This is research. And I'm confident, though, that with enough research, we can turn that potential into reality. Now, I've been doing this for a while. Here's about 14 years ago, I spoke at a Department of Energy town hall that was held at Argonne. And the title of my talk was Potential Applications of Exascale Computing in Economics. And you see the write-up in the SciDAC review as a documentation of that. So this is something I've been reaching out to computational scientists now. I guess that was 14 years ago. So this can be thought of somewhat as a progress report on that effort that started about that time. I hope that I can have a lot more to report in 2035, if I'm still here, of course. Now, let's look at the ways that the US government uses computational tools. And you will see the dramatic difference between economics and the rest of the US government. Now, the National Stockpile Stewardship Program, it has a mandate. The mandate is to make sure that if the President of the United States wakes up one day and wants to incinerate hundreds of millions of people, probably Chinese and Russian descent, or maybe Iranian, whatever, that he can push a button and in 30 minutes they'll be incinerated. Now, by the way, the Russians and the Chinese are doing the same thing. This all came out of the decision in the early 1990s to stop nuclear testing and then to use computer simulations to assure the reliability of weapons. Now, the DOE was given a computational challenge. They said nuclear weapon simulations must extrapolate far beyond the available data and must predict coupled, multi-scale physical phenomena that are difficult to isolate in experiments. And Congress demanded that the administrator for nuclear security shall develop and carry out a plan to develop exascale computing. Now, those guys, they took their mandate seriously and they got a lot of money. And so this was a machine that they had about 10 years ago. It's called Skybridge. Now, by the way, whoever came up with that name has a sick sense of humor, as well as a boss who hadn't seen the Terminator movies, which talked about the Skynet computer. But then that's an old computer, Skybridge, and now we have more recently Sierra. Neither one of them is exascale yet, but of course, there is the Aurora project going on at Argonne. So we are aiming in that exascale direction. Now, let's contrast that to the US Federal Reserve. They have a mandate also. Their mandate is to ensure price stability, full employment. Also, they are the lender of last resort. And in the past decade, they also have acquired a lot of responsibility in terms of regulating financial institutions and regulating systemic risk. Now, my view is that they should also have a mandate to use economic policy simulations, because they must also extrapolate far beyond available data. They must also predict coupled multi-scale social and economic phenomena that cannot be isolated in experiments. And so this sounds like their mandate also is an appropriate use for high power computing. What computational tools does the Fed use? That is what the Fed uses. Laptops, and then a econometric software package called eViews. The main macro model used by the Fed is something called FRBUS, FRB/US. And it is basically a slightly nonlinear set of equations that are solved by code written up in eView's code, and all handmade by, handwritten, coded up by somebody at the Fed who has no credentials in writing up software. And why do they choose this? Well, because it's easy to do programming and to create graphs in the same code. That was an answer I got. And then when I pointed out that there are many ways you can do that, they stopped answering my questions. But that's what the Fed started using in 1996 and continue today. So they aren't, that's what they use. Now, my attitude is that the Fed has a real job and substantial resources. They aren't just a bunch of economic professors blabbing on and on about this or that, et cetera. They've got a real job to do, and they've got lots of money. They spend about 50 million a year, I think, on their research staffs at various Feds, regional Feds. A lot of young people there want to have the training and the hardware to do serious work. Now, the Fed has I would not want their job, to manage the monetary policy and economic policy. That's a very difficult job requiring a lot of judgment. But when the organization doesn't really care about being good at doing the arithmetic behind their judgments, I wonder how careful they are at doing when it comes to judgments. That's the challenge that I've made to them. Now, some of you may recall from history course the famous 1896 speech of William Jennings Bryan, where he said, again, argued against the gold standard and argued saying that you shall not crucify mankind upon a cross of gold. That was the kind of rhetoric 125 years ago. But I wonder if he were here today, we'd have no gold standard anymore. But what would he say about monetary finance and financial policy analysis at the Fed, this millennium being based on laptops, using minuscule computing power, using obsolete homemade code? That's the situation we're in today. Now, okay, so that's the challenge I have laid down for economists. Now, I've had some success in using modern computational tools in economics. And so today I will go over some of them for you, giving you a quick overview of the things I worked on. Now, here is one project that I worked on for many years. It's what's the optimal carbon tax in the world? Now, this was a question that has been discussed now for many years. Nordhaus's first work on this goes back to early 90s. I believe Kevin Hassett had a paper even before that. Now in 2010, there was a joint effort on the part of many agencies of the federal government to determine the social cost of carbon. And they came up with a number, I forget what exactly it was, but anyway, they came up with a plot of numbers of what the optimal carbon tax would be throughout this century. Now, the model they used to describe the climate and the economy was very simple. Everything was deterministic. That is, everybody knew with perfect certainty the path of the economy and the climate given carbon emissions. Okay, that's a problem. I don't like that assumption. Furthermore, when it came time to discretize the differential equations that model the climate, the concentration of carbon, the diffusion of heat, etc., they used a novel finite difference method to approximate the differential equation. What they did is they used 10-year time steps. So they discretized time with units of 10 years. Furthermore, their discretization implied that CO2 emitted 10 years from now would start heating the earth now. I refer to that as time traveling CO2. Now, what I and my collaborators showed is that this created about I don't know, about a 15 to 30% error in the their optimal carbon tax numbers, higher than they should have been. Now, was this some kind of liberal conspiracy by left-wing Greens? No, it was just that these guys just didn't know how to discretize differential equations. Now, so what I and my collaborators, I list the two main ones here, Young-Yang Kai, who's now at Ohio State, and Thomas Lonchek, who now is at the University of Aachen. But at the time we did this, they were both postdocs. And so what we did is we wanted to look at what is the optimal carbon tax in the world, but where there's riskiness, there's uncertainty. We don't know where the economy is going to be over the next 100 years. We don't know where it's going to be tomorrow. There's a lot of uncertainty in the economy that has nothing to do with the climate, nothing to do with anything except it's just very uncertain. Economists model the underlying dynamics of the economy as essentially a Brownian motion with some drift. It's not a straight line that can be perfectly predicted. So we added that. We went to a model that had that kind of uncertainty in there. Then also we added things like uncertainty on the climate side. For example, the increasing temperatures is going to speed up melting of glaciers. But again, we don't know the time scale which that's going to happen. So we used expert opinions to calibrate that. So we did this and we called it dynamic stochastic integration of climate and economy. And here's a picture of the model. I normally hate pictures, but when Thomas drew this, I said, it's a good picture. So the economy creates emissions. Emissions go in the atmosphere, emissions of CO2. And then the CO2 gas diffuses between atmosphere, upper ocean, and deep ocean. And then in the atmosphere, the CO2 creates interactions with radiation and heat have increased temperature of the atmosphere, which then also increase the temperature in the ocean. And then the higher temperature damages the economy. Now, what we added is a stochastic feedback, a stochastic element here, that how much damage a higher temperature does is itself a stochastic process. Also, we also said the economy is subject to stochastic shocks. And then what happens, how do we control this? Well, we have mitigation policies that to put a lid on emissions. This, by the way, is those of you who know about Nordhaus's DISICE model. This is the same as Nordhaus's DISICE model. And he got the climate part here. He got after talking with Schneider, famous climate scientist here at Stanford many years ago. But we added this uncertainty stuff. Now, by the way, what that does is that transforms the problem from optimal control of a differential equation to optimal control of partial differential equations. That's what that transformation does. Now, those of you who know about dynamic programming will recognize this is a Bellman equation. I'm not going to go through all these equations, but this is basically discrete time optimal control where you have uncertainty. This is a discrete time version of Hamilton-Jacobi-Bellman equations. This is also a discrete time version of what's called backward stochastic differential equations. The key thing is that there's the state vector is 8-dimensional. Now, what I like to tell guys that work in PDEs is, you're probably tired of working with 3 spatial dimensions, aren't you? See, we have 8. So, that means we can give you an excuse for taking what your 3D methods for solving 3D diffusion equations and then expand them to 5, 6, 7, or 8. So that's where economics is different. It's likely to be higher dimensional problems. However, it is, in this case, it's like controlling a diffusion. So we aren't going to have shock waves like with hyperbolic PDEs. There's a smoothing element here from the diffusion operator. So going to higher dimensions is possible. And so we solved it. It's basically a difference equation in a Banach space. You have a terminal time and you solve backwards. And this is what the biggest example in the published paper. The paper came out in December 2019. in JPE, which is one of the top journals in economics. Now, the largest example, we have many examples in the paper. The largest one, 9 dimensions. We solved it, parallelization. We used 84,000 cores, which took 8 hours. If we just had a single laptop, we'd take 77 years. And my postdocs wanted to get a real job before 77 years passed. So I wanted to get something done before, because I'm not going to be around in 77 years. And now what these numerical dynamic programming problems amount to is you solve, millions of optimization problems, and then you hit a parallel block, and then you solve it. Then once that parallel block has been resolved, you have millions of little optimization problems again, and then there's a parallel block. Because we have good load balancing, the parallel block is not a problem. In fact, on this problem, Yang did some scaling, and the time scaled linearly from 10,000 to 20,000 to 40,000 to 80,000 cores. So this was something that passed the critical scaling test of does it belong on a supercomputer. Also, when we did some flops count, we found that it was 10% of peak, which we're told by supercomputer people is pretty good. So that's the kind of computational resources we used. This is a computer we used, Blue Waters, which was the leading edge NSF supercomputer for a while. It's now been supplanted by, I believe, the machine in Texas. But anyway, these things only last, they last for 5-6 years, and then they become obsolete. But we had it, we used it for over the course of about 5 or 6 years. We got about 20 million core hours, and we used it. Now, how did we use it? Well, one thing about economics is you don't know what the parameters are. Physics is easy. You have a gravitational constant. You can measure the mass of things. The speed of light, c², that's tied down very well. The fine structure constant is tied down to 10 digits, whatever. So you guys in physics, you know the parameters of your models. However, when it comes to economics, we have theories about how people make decisions, but we don't know exactly what demand curves and supply curves they're following. We don't know exactly the parameters in the underlying economy. One reason is that we don't have enough data to pin it down. The other reason is that these are people, and people are a lot more complicated than particles, and people change over time. So you've got a fuzzy kind of situation. That doesn't mean that you can't use computation. What we do is we look at the key parameters in the model, and then we look at what is a good range of values, reasonable values for those parameters. Like the discount, how much do people discount the future relative to today? And so we looked at discount rates of 0.2% up to 1.4% annually. And then lambda is the mean growth rate. And also Q is damages, how much, we don't know exactly what the damages are going to be. And of course, the thing is that in these models, the climate sensitivity is a parameter in the climate side that we have little information about. So here's a 4-dimensional graph. So basically, in this block, if Q is 0, low damages, growth rate is slow, then along this line in discount climate sensitivity rate, along this line, the optimal cost, social cost of carbon in 2010 is 40, along this line it's 80, et cetera. So you see that we can show you, for a large, in a 4-dimensional, this is basically a 4-dimensional graph. We can show you how the underlying parameters affect what the social cost of carbon could be. And yes, there are some places where you got big numbers, but they involve very high climate sensitivities, as well as very low utility discount rates. And people often argue, well, that's not plausible. Typically, people are going to argue for numbers that are sort of in the upper left-hand corner of all these boxes. And so you see, you could kind of get a consensus roughly about what the social cost of carbon is. First of all, $40 is like a minimum. And then even if you're on the conservative side of beliefs, it's a range of $40 to $80. Now, by the way, when I gave that talk at Argonne many years ago, somebody asked, are you sure you can use these computational tools to pin down exactly what the optimal monetary and tax policies are? And I said, no. We don't know the world with great precision to pin down exactly what the policies are. What we can do, and this is, by the way, the job of a lot of economists that go to Washington, D.C., is what we can do is we can sort of identify what are really dumb ideas, what are really bad ideas. That's what computation can do, is to narrow the range of policies to some range that has some plausible value. And many times you put in a policy that somebody comes up with and you put it into a computational model, and then you can use that to say, look, this is a crazy policy, it doesn't work, it backfires, et cetera. That's what computation can do, is to narrow the range of arguments. I've been at conference, I was once invited to be part of a panel that met with Treasury Secretary, whoever it was, in 2007. I forget these guys, Paulson. And so the panel of public finance economists talked with Paulson, and I look around the table and listen to what people say. I can't tell the difference between Republicans and Democrats, because when you're in a professional environment, we have common sets of basic beliefs and views. Yes, there's arguments, but when you put the professionals together, they can be those ranges can be disciplined, and nobody comes up with idiotic ideas that says, "Oh, we cut tax rates and revenues go up." That kind of stuff. That's in the political domain, not in the academic domain. So that's what the goal here of mine is to force economists, policymakers, et cetera, to write down what are their assumptions, and then see what the implications are. And a lot of times, the implications are different than what they hope they would be. And this is what's going on here with this climate change work. So what we see here is, this is an example of how our approach can alter thinking. In the world of the IPCC, for example, they love to talk about scenarios. What's likely to happen? And so the RCP 8.5 is a scenario that they think is what would happen if there's no intervention. That the surface temperature over this century will rise to be almost 5 degrees above what it was at some earlier time, at some base time. Now, what we show is that when you add the uncertainty of the economy to it, there's a strong chance, that their scenario gets sort of the expectation right. But the thing is that this is a 75% quantile. So 25% chance that it's above 5 degrees, and then a 10% chance that it's above 6 degrees. And this is the problem with talking about climate change. We don't know what's going to happen, but it's the extreme events that we have a lot to fear. And that's what we should focus on. So anyway, that's okay. That's one area where we've had some success in. I throw you some other slides of what we've done. Here's a more recent example of what we're doing: multi-objective optimization. Now, if we're going to talk about optimal policies, optimal tax policies, for example, the social planner, whatever, they have to worry about getting enough revenue to pay the bills. They have to worry about the utility of the taxpayers and of their politicians, the impact on distribution. Now, of course, engineers face the same thing when they design an airplane. There's multiple pieces to an airplane, and you have to look at what happens when you combine the ultimate alternative choices for the design. This is all what's called multi-objective optimization, where you have multiple objectives. And the purpose of multi-objective optimization is to tell you what the Pareto frontier is. So there's all sorts of stupid things that you can do to have low utility and low revenue. But what you're looking for is a frontier where you have the maximum revenue given a particular level of given a particular level of utility. That's what we want to do. And one thing you can write down is a constrained optimization problem. The problem is these things are ugly, nasty constrained optimization problems, really bad. Non-convex, it's really bad. So what we do this is with a couple of students I've been working with, is we just sample from, this is an example of a simple economy where we look at taxes on interest and taxes on wage rates. And we look at for the Pareto frontier, and then each of these dots, this is the Pareto frontier, and here's the tax on capital. So that on the Pareto frontier, the tax on capital is always basically 0. On labor, as you need more and more revenue, it gets redder and redder. And so basically what this says is that here's a scatter plot of all the possible combinations of taxes, 2 kinds of taxes. You look at the Pareto frontier and you realize, you don't want to tax interest income. It's a inferior policy. Now that was a brute force thing, and then now we're using this with Philip Mueller. We're using more homotopy path following methods to find the Pareto frontier. And here's an example there. We have 3 kinds of taxes we look at: interest income tax, labor income tax, and the consumption tax. What we find again is that when we plot out, here's the utility versus revenue Pareto frontier. Again, when we look at the Pareto frontier, capital tax is always 0. Labor and consumption tax can be mostly anything, but that's because they're kind of perfect substitutes for each other. So you can't, there's no such thing as an optimal labor tax or optimal consumption tax. You have a big menu. And so why would we argue over it? We have lots of arguments over these things, but this says that in this particular case, no point in arguing because the differences are of no importance. So that's, and within the, within this multi-objective optimization, what's going on is this: given a tax policy vector tau and some performance vector, this could be utility on average over people, or this is the utility of the people that voted for you, or the utility of the people that didn't vote for you, whatever. What you do is you take a set of vectors, a set of taus, policy, and then compute these performance criteria on that grid, perhaps using quasi-Monte Carlo sampling, because there's going to be a multidimensional sampling grid. And then you take that data and you construct an approximation of this function that maps the policy to the performance criteria. And how do we do that? Well, we could use neural nets, sparse grids, dictionaries, sharelet, whatever. You know, it's an approximation problem. So this is like a big data problem, except I don't have to deal with Mother Nature. Mother Nature is not nice. Whatever data she gives you, it's all noised up, errors everywhere. She gives you a lot of data where you don't want it, and then not much data where you do want it. You're a prisoner to the whatever data process Mother Nature came up with. No, I have big data problems, but I control the data. I choose where I evaluate the performance of tau. And so I don't have those problems because I control the data process in order to get this approximation of a function. By the way, this is asynchronously parallelizable, but you can also use low latency communication. This is ideal for high power computing. Now I have, I want to talk about one place where collaboration with mathematicians really helped. Mechanism design began with Murley's 1971 paper on optimal taxation. He won a Nobel Prize for that. Now, the problem with that theory is that, I'll speak in terms of optimization description. You have n variables, n choices with n squared constraints, and it's nonlinear. I know it doesn't matter if it's a linear program. No, this is nonlinear. you have massive failure of LICQ, linear independent constraint qualification. And so when Chae-Lin Su and I worked on this many years ago, 15 years ago, none of the solvers worked. A few kind of worked a little bit, but they all ultimately crashed on this failure of LICQ. And then I got the attention of Michael Saunders and a student of his, Ding Ma. And they told me, oh, Ken, we can handle it. It's easy, it's easy. Oh yeah, we got these ways. Well, so we met several times and nothing they suggested worked. And then they went away. And I thought, okay, they've given up on this. 6 months after they went away, they came back and said, hey, Ken, here's a paper where we solved it. And here's the paper, stabilized optimization via an NCR algorithm. So those of you interested in the optimization stuff can look at it. But this was a case of where in economics, this very important kind of problem has a massive degeneracy. And my name is on the paper only because I basically bugged the mathematicians about how your stuff doesn't work, which I thought was kind of nice. If I bugged the economists about stuff not working, they generally go to hell. But no, the mathematicians took this as a challenge and they delivered. And so now we have a tool to examine a wide range of phenomena that we weren't able to before. Now, I'm going to skip through the next couple things. Solving polynomial systems. Economists just always use linear demand curves, linear supply curves, because the lines cross. Linear systems are easy to solve. But you give up a lot of realism when you go to lines, straight linear systems. My friends and I have used things like Bertini and PHCPAC, both of which have a Chicago area origin. Also, I and a student of mine are working on applying modular Grosvenor basis methods with supercomputing to get Grosvenor bases. All of this is highly parallelizable. And this can basically take us to solving far more realistic systems, particularly in antitrust analysis, et cetera. I'm actually going to hit my 40-minute mark. Computational science is moving ahead very rapidly. One thing I plotted out for another presentation was, we all know about Moore's law. Speed is increasing at doubling every 2 years. What's amazing is that the cost of a gigaflop is falling more rapidly than that. If you look at the cost of a gigaflop from 1980 until 2020, or actually, I think the numbers were actually 1985 to 2017, the cost is falling at a speed 100 times faster than Moore's law says the chip speed is increasing. And to an economist, it's the cost that matters. We now have massive parallelism, GPUs, cloud computing, high throughput computing, new algorithms for a variety of things. By the way, I should say, I forgot to mention this. We are using Python. Philip Mueller is using Python to do this. The other stuff was mostly Fortran, but that's because we started, 10 years ago before Python was around even. There's new software like Python to use. I use Mathematica a lot. So the range of software tools has exploded. Algorithms have exploded in terms of the variety and their power, and economics is not using it. And so my point of this talk is to show you not so much brag about what I've done, but about how much I haven't done, but that with your help we could do a lot more and a lot better. Thank you.
Thank you, Ken. That's a very interesting talk. We have one question in the chat from Fred Hicknell.
Oh, yes, yes.
Yes.
Okay.
I believe he's referring to slide 42.
Yeah. Now, typical, the thing is, of questions like that. Yeah, he's asking for your basic task slide. Can you indicate what the typical dimension of tau is? How much data can you afford to approximate? Anyway, the problem that we're aiming at I'm working on with Philip, that is kind of like a big problem, a major problem, is 10 dimensions. Basically, we're trying to look at a piecewise linear income tax code. So piecewise linear with 5 brackets and then 5 breakpoints. That's 10 dimensions. And that is, I think, for a lot of these, for that problem, that you need that many dimensions. But now 10 dimensions in using quasi Monte Carlo methods, we can probably do 10 dimensions is not an enormous range to get a nice sample of points in 10 dimensions. Now, how much data can you afford to approximate your, the thing is that right now, I don't know how much data I'm going to need. The thing is right now that for that income tax case, I'm sure we're going to need billions or trillions of little taus or cases. You see, with each tau, then we have a lot of different kinds of people. So we may have like a million different taus, and then have like 1,000 different kinds of people, and so that's a billion combinations there. But the thing, oh, by the way, here's the key magic here. Once you specify a policy tau and an individual's demand and supply curve, essentially, then it's a convex optimization problem. And so, those things are fast. Those things are lightning fast. So I think that's that. I'm not worried about. I'm not worried about needing too much data. The thing is that surface is going to have it's going to be piecewise C infinity, but there will be places where there are kinks and even discontinuities. Now, okay, so that's why I have to hesitate. Can I find those discontinuities and kinks in high dimensional space? I don't know, but remember the focus here is going to be on Pareto efficient combinations of policies. And so a lot of times these kinks and whatever are going to be in regions of the policy space that are totally irrational. So, but yeah, there's going to be problems approximating this, and neural nets may come in handy. Basically, we have to find out. This is where it's research and exploration. Okay, so Jim Plaxco, are you familiar with a book?
I'm sorry, can I just follow up?
Yeah,
I just didn't quite understand. Normally, when you want to approximate a function rather than just evaluate it and be happy with what the values, it's because the function's expensive. So you're constructing a surrogate model, but you tell me you're going to have billions of values. That doesn't sound like you want a surrogate model.
Well, I'm just saying that the amount of use that I'm going to make of that function is going to be, it's going to be far more economical for me to solve, let's say, like a billion cases than to then go to an application and then use a surrogate and then go to an application and a variety of applications where I need to go then do trillions or quadrillions. So no, I understand. Yeah. So the thing is that the thing about this surrogate function is that I'm thinking of using it for a variety of purposes. For example, predicting, like if there's a vote between policy 1 or policy 2, it can be used for that. So the purpose, having this one surrogate function can then be used for a variety of applications in political science analysis, what I'm talking about. No, I see your point, but the thing is that in economics, that surrogate function can have an enormous variety of uses. And so the surrogate approach is appropriate. I am not familiar with radical uncertainty decision-making beyond numbers. Now, my initial response is, how do you go beyond numbers in economics? I mean, now what here's a quote from LBJ. And for you young people, when old guys like me say LBJ, I'm not talking about LeBron James. I'm talking about Lyndon Baines Johnson, okay? I've had to make that distinction sometimes in speaking with the young people. So some economists came to him and gave them a range of their predictions about what could happen. And LBJ said, I don't want ranges. Ranges are for cattle. Give me a number. Well, that's a problem in a lot of contexts. People want a number, a number, a number. We're going to have to like get them away from that, because there is no one number that summarizes any research. It's a range of numbers. So, so that's what I think. What I have some expertise in is helping people understand what a reasonable range of numbers are for predictions of what policies work and what they don't. I'll have to take a look at that, what he means by it's very popular to say, oh, I go beyond numbers. You go beyond numbers, what are you doing?
Yeah,
Anyway.
Mervyn King is one of the authors. I think he's from the London School of Economics.
Yeah. No, I've even seen Mervyn talk a couple times, met him, yeah.
He's challenging, I think, expectations that are being placed upon the models, and
yes.
the single number aspect that you just mentioned with respect to LBJ also figures into it. And he's distinguishing between what he calls small world models, which are models that have a finite number of states, finite number of outcomes, finite number of parameters, and then contrasting those with what he calls big world models, which are economics issues where you cannot perfectly model an individual's behavior or a society's behavior. And I think he's asking us to have a little bit less confidence in the numbers that these models are producing.
Absolutely. Like I said in 2007, I have no belief that I can tell you what the exact policy is. What I hope to be able to do is identify bad ideas. And I think what's needed on the part of economists is a lot more modesty. Now, by the way, I also like to remind physicists when they talk about how great physics is that I believe at last count, they only understand 5% of the mass and energy in the universe. So the rest is dark. Anyway, so many fields have some ranges of uncertainty, and you have to focus on what you can do and what you can analyze and what you can think about. I think, for example, the financial crisis of 2008, and I think many people would agree with this, was a direct consequence of this gross over-reliance on some free market ideology that took over, that basically swept away a lot of sensible regulation in the late 90s. And it was an ideology without any numbers behind it. Many of us could imagine that, could have come up with models to say that, you know, this isn't such a good idea always. So that's, I think, a case of where the lack of modesty and the domination of ideology really hurt. And so that's what now, by the way, I'm at the Hoover Institution. Everybody thinks I'm a hardcore right-wing Republican. No, I'm a lifelong Democrat, maybe on the conservative side, but anyway.
So you had some interesting conversations with Mr. Soul.
Mr. Soul doesn't have conversations with most anybody. He's a very reclusive person. I did have some great conversations with Ed Teller many years ago, and with many other people. So no, it's a lot more open-minded than you might, than the image is. And that's, within that context, that people understand, yes, we don't have we don't have total confidence in everything that the pure theory says. And the thing is, one of my professors in graduate school was a guy named William Brock. And one thing he said to me is that, mathematicians have seen all of the assumptions that are behind the free market economics ideology. And that's why they tend not to be conservatives and free market advocates. They've seen all the assumptions that go into argument, the standard Chicago style economics. That's a lot of assumptions. It's a good starting point, but to be the end point is not a good idea. And no, you have to realize that the world is not perfectly competitive with zero transaction costs and all sorts of other simplifying assumptions. But one reason why economics really is stuck in the simple world is because it refuses to do this kind of analysis. It's stuck in the second millennium, where everything had to be done basically in pencil and paper. And whereas, you look at papers written in economics in the 1970s, and then what they're written today, the mathematical complexity is surprisingly similar. They just haven't adopted the 40 years of progress in computational science and applied math. And that's what I've been trying to do. So, yeah.
Follow-up question. Why do you think that is?
That's not a suitable topic for a scientific talk. Now, one thing I want to, by the way, I think my official time is close to coming to an end. I will be here until 7:30 your time. But I just want to end by saying, I welcome more conversations on this. I hope this is just the beginning of many conversations with this audience. Anyway, if you don't have my email address, just do a Google search for Kenneth Judd. You should find my webpage somewhere. Maybe Sue Cheng can send out my email address. Actually, one of the email addresses is easy, kennethjudd@mac.com. The other one isn't hard either, judd@stanford.edu. But anyway, please, if you have any comments, questions, email me. I love to take up many more topics of conversation with all of you. But I think this is the official end of this presentation, and I thank you. But after Sue Cheng is done, then with the official end, then I'm still here.
Well, thanks, Ken. There are two more questions in the chat window. One more from Jim.
Okay. What is your view on the current state of, okay. Machine learning in economics is largely confined to empirical work. I have some colleagues at Stanford that do a lot of this. And they basically are using machine learning, deep learning to analyze data in a sort of basically what they're doing is a fancy version of regression. One thing I like to point out to economists, they start talking about, they read all the propaganda in neural nets and all that, and I say, it's just another form of nonlinear regression. And so that's now one reason I say that is because I remember the big rise in popularity of neural nets in the 1980s, and then that bubble burst. So anyway, now there are some friends of mine that are using neural nets to solve, basically in science, some people are using neural nets to solve partial differential equations. And then some of these things I've been talking about are kind of like solving PDEs. And so neural nets could be used to do that. I don't know how good that method is going to be, but we'll see. No, I think the machine learning and I mean, it's like I said, a lot of this is very advanced, powerful ways of approximating a surface, given the data you have. And so that's how I view all of these, as just better ways than orthogonal polynomials for many reasons, better way anyway. So better than Fourier approximation, but I put them all in that. And in fact, in the next edition of my book, I'm going to have 2 chapters on approximation, classical methods of approximation and modern methods of approximation. But it's all approximation. You have data, you have points, and then you try to find some manifold of some dimension that represents it. There was another, okay. Regarding next steps, what is your, that's for another conversation. That's to email me. No, I mean, I think there's the story with Michael Saunders and Digma and Orban. I mean, it's a great example of how collaborations can yield to progress for both computational math and for economics. If you want to hear more about my call to action, then follow my blog starting in a couple of months. But no, right now, I mean, if anybody has some ideas related to this, just contact me and we can chat.